So today we'll be coding our very own virtual machine, complete with a virtual CPU and virtual memory. It will have a 16-bit CPU and 6 different CPU registers. We'll also need to develop our own assembly language with instructions like move, no op, halt, etc. We will have 65 kilobytes of virtual memory, and it's going to be divided in a code segment, which is read-only, and a stack for data. Okay, let's start the project. What's up, guys? Welcome to today's show. Today we're going to do something very exciting. I am gonna code a virtual machine, and I have never done anything like that before, but I have a general understanding how we should do it, and let's see how it goes. So let's get to it. I will start by logging into my CodePlanet server, and you know you can get access to this Linux server if you become a member, if you become a tier 1 member. Enough advertisement. Let's see how we're gonna do this. I'm gonna go into my folder and I'm gonna use our own build system, bash bs. And if you remember, bash build system is a tool which generates the .c and .h file, a basic starting point based on a template. And if you want to get bash bs, you can always download it from the repo.drbirch.com. A lot of stuff here is not always available, but bash bs is always available, and so is the birchutils, which I use quite frequently. And also all the code for this episode will be available for 48 hours after I publish this video. If you want older stuff, you need membership. Alright, so let's see. I will run bash bs and I will call this project. What should we call it? What about Birch VM? It's not a great name, but I'm not coming up with anything better currently, so. And which template? We only have one, default C template. And there we go. If we go into the Birch VM folder, let's set this to our home. We do have a makefile, a .c and a .h. So let's launch Sociopath ICP client, one of my best programs that I made, I think. So I will go into the TNP and I will right click on Birch VM and open in editor. So now it will download everything and it will be synced, so whenever I save or create a new file or a directory, it will automatically upload it to my Linux server, CodePlanet. So let's see, is this correctly sized? Pretty much, yeah. So let's see what we got. We have a simple makefile which will compile everything with birchutils. We have a very simple .c file which only includes the h and a tiny main function. And then we have the h file which has a bit more, a couple of includes, including the birchutils. And then I have my integer numbers, and I have my typecast macros. But one of my viewers asked me, why do I name this after the So the 6 is the 6 here, and the 2 is the 2 here. Isn't it better to name them after how many bytes they are? And indeed, that is a better way. So this is 1 byte, this is 2 bytes, this is 4 bytes, this is 8 bytes. So thank you for that. That's a great suggestion. And if you have any suggestions, please put them down below in the comment section. I mostly listen to all my suggestions. Alright, so let's say this. How should we create a virtual machine? What is a virtual machine? Well, basically it's a computer. So it has the same thing a computer does. It has a CPU with different registers and so forth, and it has memory and perhaps any auxiliary ports, etc. So let's start simple and build from that. That's usually the best way to approach this. Since I have never coded anything like this and I haven't really planned, I will just do as I go, so to speak. And as always, I begin by creating the data types. I'm letting the data types guide the entire project. And that's a good way to do any project. Because if you have all the data types, you only need to create the functions that use these data types. And you're done. Alright, so we need a structure for the actual virtual machine. So let's call this VM. And what does a virtual machine contain? Well, it contains a CPU, right? C, and some memory. Let's say we have a shall we just name it memory and then divide it into different sections and stuff, or should we just use stack? I think we are going to use stack for now, at least. If we need other types of memory, that's a later question. Alright, and let's see. I'll make this a pointer so we can... by the way, I have some limitations with this project, so it will not be too difficult. This virtual machine will be a 16-bit virtual machine. So like the 386 computer, if you had one of those back in the days. And 16 bits, that's basically 65,536 different memory addresses or different possible values inside of the registers. And that means our memory will be 65K. Yeah, so 65 kilobytes of memory. And our CPU will have a couple of registers, and registers are basically the processor's memory. So we will have an AX, we will have a BX, a CX, and a DX. So these are the general purpose registers that we use for like addition and stuff like that. But then we need a couple of other registers as well. We need a stack pointer, which basically points to the top of the stack, the memory. And we need a instruction pointer, IP, which points to the next instruction in the program to execute. And we could add a lot of other stuff here, but let's make it simple, and I think we will start with only this stuff. And then I will probably add some kind of, I don't know, a serial COM port or something, but that will be a later question. And possibly a hard disk drive, or maybe a floppy drive, something like that. But this will also be a later thing. So the first thing we are going to focus on is getting the CPU to work and the memory, right? I'll keep them here as for now. So we will have a CPU and a stack, and we also need a program P. So basically a sequence of different instructions. Right, so let's start there. And I want to type this struct, so struct svm, and this will be a VM, like this. Okay, but what is a CPU, what is a stack, and what is a program? Let's begin with the CPU. This will also be a structure, SCPU. And as I mentioned before, we need a couple of registers. So registers are, or maybe we shouldn't, should we have these many levels? Maybe we can create macros to make this a little bit easier later on. I think the structure will be better if we do it in this kind of way. What else do we need in the CPU? Maybe we should just start there. So we need to type def our struct SCPU, and we'll call the CPU like this. And then we need to create the registers as well, which will be a different structure. So registers. And as I mentioned before, we will have a couple of different general purpose registers. So let's say this is reg, and we will have, I will use lowercase for convenience. We will have AX, we will have BX, we will have CX, and we will have DX. Those are the general purpose ones. And then we need the stack pointer, and we need the we need the instruction pointer. And this would be enough for now. Type def struct s registers, registers. And what is a reg? Well, for now, or possibly forever, this will be an unsigned short int, because we are dealing with 16-bit registers, right? Okay, so that part is done. What about the stack? What is a stack? Well, basically it is a memory space. How shall we define the stack? Perhaps we will just do this. It will be an, let's see, it will be a sequence of 8-bit characters. So we'll only do this, I think. So stack will be an int 8 basically, or several actually. It will be an array, but we will not define, or perhaps we should actually. Maybe we should not make this a pointer, but we will do, can we do this? I'm not sure if this is possible, because I want basically this, right, all ones, and that is the same as this, but I'm not sure if that is correct. We will see if it works. It would be kind of cool if it worked. Alright, so let's see, we have the stack, and what about the program? What is a program? It's a sequence of instructions, right? So basically we will type def a sequence of instructions. So instruction, and this will also be an array, but we will not define its size. So I will only do this, and now we need to define what an instruction is. And what is an instruction? Well, it's something which will look, basically, an instruction is a sequence of opcodes, right? So let's define that. So type def opcode. Opcode, that is basically the machine code version of the assembly instructions, because we need to invent our own assembly language in order to make this work. It will be a basic assembly language, but it will be our own. So let's see, type def opcode program, and since program is a pointer, this will be an array when we use it. And what is an opcode? The thing is, opcodes look a little bit different depending on, they have different size, for example. So let's say we have something like move to the AX register number 5. How will this look like? First we will have something which defines that it's a move instruction. So let's say, for example, 01 is a move, and then we need to define what the that we were moving to the AX register. So we could do something like another 01, which would suggest that this is the AX register, but I think a better way would be to take this 1 and do some mathematical operations to it. So let's, for example, say that we do an OR operation, and then we have this AX thing. And if we go and check out the binary representation of this, so we have 2 bytes to use, which basically means 4 hexadecimal characters. So if our move instruction is a 1, and the different, let's see, so the rightmost byte, if that is a 1, this is a move instruction. Or maybe if those 2, let me see, we actually only have 1 byte at this point. But 1 byte if we look at binary, it's this, right? 8 bits. So this is how we should think of it. So the move instruction, let's say the move instruction is defined by putting a 1 inside of the rightmost 4 bits. So then the rest of these bits can be used to define what we are moving to. So let's, for example, say that this, if this is a 1, then we're moving to the AX register. If this is a 0 and this is a 1, we are moving to the BX. And then we have CX. We have DX. We have SP, that's the DAC pointer. And we can't move anything to the EIP instruction pointer. But it seems that our bits will will be enough here. So this rightmost 1 should be a 1, defining that it's a move instruction. And those 3, we will use this OR operation. So if we want to OR it with AX, and we have this, right? This is the move instruction, and we want to flip this byte to 1. And we will OR this by 02. That will flip this to a 1. So that's basically how it will work. And if we have an entire, and the 5, by the way, how do we put the 5 in there? Well, we have these 4 untouched bits. And how many combinations is that? That's 2 to the power of 4, right? And what is that? 2 times 2 is 4, times 2 is 8, times 2 is 16. That's not enough. So basically, we need, how much do we need? We need an entire 16-bit thing, right? So this first byte is a move instruction. And then we need 1, 2, 3, 4. 1, 2, 3, 4. And we need 1, 2, 3, 4. 1, 2, 3, 4. We need all this to define the 5. If we are going to be, if it's going to be possible to use all the 65,000 different combinations. So in this case, to get the 5, what do we need? We need 1, 2. We need this to be a 1. So we have 4, and this will be a 5. So this whole thing together will be a move to the AX register number 5. I hope you were able to follow along. And if not, try rewinding and listen to this once more. I think you will get the idea then. Otherwise, you will definitely get the idea when we start coding this thing. Because then it's not as abstract as it is at this point. Okay, so program is a sequence of opcodes which can be a variable length. So we need to define, no, it's not opcodes, it's actually opcodes and arguments, right? Because the opcode is just the AX in this, the move AX in this case. Okay, so instead of making this a sequence of opcodes, we need to make, let's see, right, we need to make this a sequence of instructions. And we need to define what an instruction is. Instruction is basically a command to the CPU. So the first part will be this, the actual opcode. So we'll have an opcode O, and then we will have a variable length of arguments. So let's say args A, and this will be an array with a non-predefined size. So this can be basically 0 to 2 bytes as arguments. We'll type def struct as instruction, and now we only need to define the opcode, and let's make that an enum. So let's see. Maybe we should have some kind of table which tells our virtual machine how big this instruction is, right? Because all those instructions will be of different length. So we need some kind of table which tells us that. So instead of opcode, what should we call that? It will be the actual instruction. Maybe we should just name this a little bit different. Let's say a program is an instruction sequence. So instead of a singular instruction, this is an instruction sequence. Let's say this is an instruction sequence. This too is an instruction sequence, and this will be how we do this development. We will take 2 steps forward and possibly 1 step back, and then edit some stuff and then move forward again, because I'm not sure how to do all this stuff. We need to figure it out as we go. Alright, so now we have an instruction set. An instruction set will have an instruction I and arguments A, possibly arguments A, and this will be the struct S instruction, and here we will have an opcode O, but we will also have a, let's see, am I making this too complicated now? Maybe we could just pass the opcode to a function. It will look inside the table and tell us how big that instruction is. Yes, let's move back a little bit again. I hope you bear with me. Okay, so a program is a sequence of instructions. An instruction is an opcode with an possible argument. The opcode is an enum s note e opcode, and we will have a whole lot of these, but for the time being we will simply have, and I never seem to remember the order of this thing, but the compiler will help us. So we'll have a move instruction, which will currently be 1, but we will, I will probably change that later on to match the Intel specification. But for now it will be 1. And what else? We can have a no up, which at this point will be 2, and let's start there. And we will type def our enum e opcode to just opcode. And now we have all the different building blocks, right? So let's create the table of opcode to size, so we know how big this thing is. And how should we do this? Let's see. Let's create a structure. I like structures. Is that showing? So let's call this instruction map, and it will take an opcode O and a size. So this will be int 8 size. And possibly we'll have something more in this thing, but for now this is enough. So type def struct s instruction map, and we'll call this IM. So let's go down here and let's create this table, and this will be a static thing. So let's say we do static im instruction map equals, and now we will have those different things in here. So first we will have let's say, how will we refer this? Let's use our enum. So this will basically be opcode dot move, and the size of the move will be 5 bytes. No, 3 bytes. Let's see. Let's double check. First we have this, which defines the actual move instruction. I'm not entirely satisfied that we lose these 4 bits, but let's do this for now. And then we will have 2 additional bytes, so 3 bytes. And we will also have the opcode no up, which will have a size of 1. This should be possible to do like this, right? Let's try to compile this and see what happens. Okay. Unknown type name opcode at line 67. Because we define this below. This is 1, 2, 3, 4, 5 lines. Let's try this again. So we do make clean, we jump down a little bit, we clear the screen, we run make, and boom. Still some errors. Unknown type args at line 80. It's also always a little bit difficult to put these ones in the correct order. Okay, we haven't even defined those args. Let's do that. And what is an argument, singular is? Well, it's basically, let's see, a sequence of bytes, right? So let's do type def int 8 args. So we make clean, we jump down a little bit, we clear the screen, and we run make, boom. Okay, it didn't like our minus thing there. Let me just try one other thing before we fold, so to speak. If we put this inside of a parenthesis, and before this we do unsigned int, unsigned int this, and then we put the whole thing inside of a parenthesis as well. Alright, if it works, it would probably work this way. It seems like it did. Isn't C a beautiful language? Alright, what does it say here? Braces around scalar initializer. Okay, 97. Okay, so static IAM instr map equals this. Okay, it doesn't like being a pointer. What if we were to do this instead? Okay, now we're talking. Okay, we can do opcode.move. How do we reference those enums? I never really learned how to use enums. Let's see, enum e opcode, and we type def this as opcode. Do we need to create an instance and reference that? Or can we do e opcode dot things? Let's try that first. So e opcode and e opcode. Nope, can't do that either. That's a little bit annoying. So what use do we have of these actual enums? So we have enum e opcode contains this thing. Do we need to create an instance then? Let's try that. So if we do static opcode I'm not sure how to do this properly. This doesn't seem quite right either. But let's try it again, at least. Request from member, move in something, not a structure or union. Because opcode is defined as enum e opcode. Isn't the whole point that we should be able to reference it with a dot? I will consult Google, I think, in this case. Google, and we check for C union. No, union. Wait a second. Did I say union only now, or did I actually? No, it's enum. Let's search for C enum. Let's check this out. Annoying pop-up. Okay, so enum level. Enum level my var. Enum level my var equals something. And then we can access my var. Enum in a switch statement, enum level my var equals median. Okay, maybe we can just do this, right? Instrument defined but not used. Opcode defined but not used. Okay, we are alive and kicking, ladies and gentlemen. Wasn't this kind of beautiful? I think it's beautiful, right? So let's make this code look a little bit better as well. Let's move this together, and this to struct. This is one thing, and let's have a space there and put this together. This is okay. Let's move this together. Then we have other type def. Let's do this, or no. Tough one. Let's do this. Isn't this really, really beautiful? So struct svm, and then we have that. Let's move this together. And now we have something. Okay, let's make a constructor function for creating a virtual machine. So what shall we call this. It will return a VN, a pointer to a VN, and let's call it virtual machine, right? And we don't need to give it any arguments because this will just create an empty thing. Alright, so let's define this function, VM virtual machine, and no arguments. We will have a VM or a pointer to a VM. We will also have a size, and the size will be equal to the size of a struct SVM, and the P will be equal to a VM casted malloc call, and we will send the integer value of size, and we can assert that we have a P, or no, let's make this a little bit more portable, I think. So if we don't have a P, what shall we do? Maybe we should do something like setting the error number to some constant, maybe none, or just rmen, and then we will simply return a VM casted 0. So let's create this error thing. So we define error mem as 0, 1. And can we think of any other errors at this point, creating an empty virtual machine? Probably not, right? Okay, so what do we do next? We will zero out this thing. It's probably 0 anyway, but let's make sure. So we will send an int 8 casted P and size. So now we have 0 structure, but we need to do some more steps, right? So let's see what we have currently. This is what we have. So the CPU is probably not much we need to do. Let's see, where do we have the CPU? Right here. It has a couple of registers, and all of those will be 0 from start, which is fine. Alright, so that's nothing we need to do about. Then we have a stack. And what is a stack? It's 65k of bytes. And that is also not anything we need to do. The program, however, there we need to allocate. Maybe we should supply the program to the constructor instead. I think we will. So it'll take one argument, which is a program, or rather a pointer to a program. So let's go in here and we say program PR, and what shall we do with this program? We need a size of that program as well. So let's say int16 size. No, size is already in use. Let's call this well, let's call this program size. And let's not forget to update our signature. So this will be an int16. And we could just use this pointer and put it inside of our struct, but we don't know really what this is coming from. Perhaps this is something on the stack in a function somewhere, and then when the function terminates, this memory thing will probably not be available. So the program should be copied to a safe place, right? So let's do some sanity checks in the beginning, by the way. Let's assert two things. Let's assert that we have a program and that we have a size which is not 0. That is basically all we need, right? Yes. Alright, so at this point we can, let's create our own program pointer. So program pointer, and we will allocate the necessary size, which basically will be pp equals the program, and we do malloc, we send an integer of the program size. If we don't have a program pointer, we will free up our virtual machine. We'll set error number to error mem again, and we'll return a virtual machine cast at 0. If we do have a pp, we want to copy that program. So there is a mem copy thing, but it would be kind of interesting to write our own, right? So let's just call this copy, and the destination will be our program pointer. The source will be this program, PR, and the size will be program size. And now we are ready to return this P. But we need to make this copy function. And I don't think I want to put this inside of this project. This is a function which will probably be used many times. So let's put it inside of lib-birchutils instead. So let's go to sociopath and our code and birchutils, And let's open this too in editor. And let's see, I will simply do this. I will take this whole thing and put it inside of here. So we can close this one. And now we have access to the birchutils. So let's see, before we do any changes, let's modify our makefile. So we are using the latest version, and we can do this. Let's see. Let's make a copy of this and comment out one of them. And this will be without this. And let's see. Birch VM will depend on my home directory, my code birchutils/birch utils.o. Let's copy this thing. And we probably need to put it here, right? So let's see, we only need the first one, but we also need this. Because I want this to be automatic. I don't want to go and manually compile birchutils all the time. So this depends on, let's do this, and so, and this, and let's change this to a C, and let's change this H. Alright, so what do we want to do with this? We want to save our current working directory. So let's say current working directory is equal to how do we do this? I think we can just do, I'm not really sure. How do we execute? How do we execute? Maybe we just, no, I'm not sure actually. Because I wanna, never mind, let's just do this. It's equal to pvd. Then we cd into let's copy this path, let's put it back. We cd into this path. We run make, and we return to the saved. To the saved working directory. Will this work? I'm not very used to this kind of multi-level makefiles. Okay. Let's fix those errors first. Conversion from long unsigned int to int 16. Okay. I have never seen size of complaining before. That's interesting. That must be because I have the newest GCC. This will probably not be in your environment. Let's see. So where did we reference that size of? It's right here. So let's make this 16-bit size of. All right. And what else? The copy. It complains about the copy, but we haven't created that yet, so that's okay. But let's remove it for now. And what else? Define but not used, define but not used. I don't care. Why do we get an error? Oh, here is something. PR size. Undeclared. Right, it's prog size, not PR size. So, prog size. Didn't I say? Prog size. Save. Is something wrong with this? No. It did update. Is this another line perhaps? 18. This should be prog size as well. And now I think it should compile. Yes. And what if we make an alteration into the birchutils? Let's just add a space here. I'm not sure if that's enough, but I think so. And if this works, it should recompile the birchutils. Okay, that's quite of a loop there, guys. I have never seen anything like that. How is that possible? Okay, let's check out this make file. So what are we doing? We're running make inside of that directory. And let's double check the dependencies here. So in order to make this .o, we need that C file and we need that H file, and then we get the O. And in order to make birchvm, we need that O. So why does it loop? Let's do something like read x here so we are able to see what's happening. Let's run make. Okay, that didn't really do anything. Let's scroll up instead. So what does it do? Okay, perhaps it's because we run the clean, but no. Let's try. What happens if we do this? No, same thing. Okay, this is an unusual type of error. What's happening? Entering directory. We set this. We cd into birchutils. We run make. Okay, maybe No. What if we were to change this to make birchutils.o? What would happen then? And let's run make clean, and now we do make. Okay, that's better. So we go into birchutils, no rule to make birchutils.o. Maybe we need the entire path, but do we really? What if we would, maybe make is smart enough to understand. If we just did this. So we make birchutils.o, but we just mention the entire path right there. What happens then? Make clean, and make, and then we loop again. Yay! Directories. Let's just do a simple Google and make file in another directory. Accept and remove all those annoying pop-ups. Why don't they make a pop-up blocker that deals with the new kinds of pop-ups? CD blah 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 and make. Interesting. So CD this. By the way, this should also be inside of the parentheses. Let's try the solution. Make clean, jump down a little bit, clear the screen, and we run make. Can't CD, oh, that's right. It's a little bit tough to CD into an object file, right? Rookie mistake. Shame on you, Dr. Birch. Make clean, jump down a little bit, clear the screen. We run make, and boom. Now it works. It recompiled our birchutils, and it used that in order to link this thing. Great! Thank you, Internet. I had to break my no Google rule in order to fix this, but it's all for a good cause, right? Alright, so let's see. We have birchutils.c, let's put it there. And makefile we don't need, and let's also open the O file. And as I usually do, I will update this version number so both you and I have a little bit more knowledge, right, about which version we're dealing with. And let's see, we will create a copy function, so a new section of character C. I have made those labels for the different starting character of the function, because this will probably be a lot of functions in a couple of years, right? All right, so we'll have a void copy, which will take a void pointer, or maybe it will be easier to do an int8 pointer. This is the source, this is the destination, and this is the size. And should it make it for bigger sizes than int16? I don't know, but let's not at this point at least. It's very easy to change. Alright, so how do we make our own memcopy function? Shouldn't be too hard, I guess. I've never done this, but let's see. So copy, and we will have a destination, and we'll have a source, and we will have a size. And what do we need? We need a pointer, p. We need int16, n, and a for loop. So we set n equal to size. We set p equal to the source. Right. Maybe we need 2 pointers. Let's call them destination and source. So our destination pointer will be equal to the destination, and our source pointer will be equal to the source. That's our starting point. We're going to loop as long as n is not 0. And at each iteration, we are going to decrease n, we are going to increase d, and we're going to increase s. And what are we going to do at each iteration? Well, we're going to set the current destination byte equal to the current source byte. And that should be it. Okie doke. Let's compile this thing. So we run make clean, jump down a little bit, clear the screen, and run make. And this is a little bit annoying. The snprintf function in this case is not truncating anything. So I want to get rid of this message, and I never seem to remember how to do that. I have some example in my code somewhere, but where? Let's go into my home directory and code. Let's search for push, and at the same line we need a pragma. Okay, maybe we should just search the C files, or H files rather. So let's find -name any.h file, and we want to execute grep based on that file. Do we need to escape those? I never remember. Something like this, I guess. worked, but we didn't get the name of the file. Okay, so let's grep the search file and some other file just to get the names right. Alright, catch-22c, there we have it. Let's open this thing, and we have, where do we get, here it is, perfect. And then we have a pop at the end or something, maybe it's inside of the C. Yeah, pop. Okay, makes sense. So let's go into our lib-birchutils and add a couple of more progmas. And the truncation is what we want to get rid of. Let's remove this annoying M right here. And at the end of the C file, we'll put this push thing. We say this, and let's try make. Okay, that's a little bit easier on the eyes, right? A little bit easier on the eyes. Alright, welcome back you guys. So, what's next? We are able to create one of these things. Let's use our copy function. And maybe we should try this out so we know that it won't crash. And maybe, or probably, it will crash, since memory operations always, or at least many times, result in a seg fault before you have fixed it. That's the ugly truth, but I think it will work out of the box. So let's create a VM, and the VM will be equal to a virtual machine, and we need a program. And what is a program? It's something like, yeah, what is a program? Program. Where do we have the program? Program, show your face. Here you are. Type of instruction. Alright, it's a sequence of instructions. Instruction is this kind of thing. Opcode and args. So let's see. Let's say we have a program which will be equal to, well, let's do this. Program proc. And the prog will be equal to example program. A little bit more structured approach. And this is a program, example program void. And since this is an example thing which should not be in the production code, I will just make a little space here, which will make it very easy to differentiate later on. Those small little hints are very useful, I believe. So, a program is a pointer to our example program with no arguments. And how do we define this? Let's do static program proc, or it needs to be a sequence. Okay, let's do this instead. I think we can do that. And what's in here? So first we have the opcode O. So dot O equals, and I think we can just do move, right? And what's the next part? It's the argument. So the A is another array, which will be a sequence of bytes. So let's say we move the, let's see, we want to move a 5 into the EX register. That means that the first byte will be 0 and the second byte will be 5. And let's have one more. So this is our first program. Let's do this, by the way. Maybe we need to do one more level. I'm not really sure. I usually don't code this way, but I think it's a good way to do this. So if we have this additional level, we should be able to do this, I think. And this time the O will be equal to a no op, and the A will be equal to no args. So let's define a constant like that. And this is where the line ends, and then we'll simply return this program, right? I think this should be the correct syntax, but I might be wrong. I might indeed be wrong. So let's see, what are no args? So let's define no args to be it should be a 0, but it should be a 16-bit 0. So how to express that correctly in C? I think we have to do this. Okay, so when we have the virtual machine, or maybe we should start with the program. Let's print out the pointer so we see that it returns correctly. And this is the group. And let's do the same for the VM, right? So this is the VM space, and then the VM, and we return 0. All right, let's see what kind of errors we get, because I sense we will get some. So let's make clean, let's move down a little bit, clear the screen, and boom, as I thought. Implicit declaration of copy. And that is because we are including the wrong birchutils H, I believe. The old version. Yes, yes, yes. So maybe we should... If we do this, and we alter our makefile a tiny bit, so let's see, no, this is the wrong makefile, this is the one. So we add a flag, and let's not do C2X, by the way. Now in the latest version of GCC, which is no, I have the old version on this machine. Bummer. Never mind. Let's add a flag, and I think it's big I for include directory. So let's select this directory. Like so. And now I think at least that error ought to be wrong, ought to be away, gone. Yes, it is gone. But it doesn't like our argument types, which is sensible. So let's see. In here we make it to in date. So let's do the same here. Everything is a sequence of bytes, right? So let's make this a 1, and this is also a 1 byte thing. And one error should be gone. Okay, initialization of flexible array member in a nested context. What does that mean? Initialization of flexible array member in a nested context. And that should be something wrong, that we have it in a nested context. Because this program is basically an alias for instruction. An instruction that is a structure which has an O and an A. So it's a structure which has an O and an A. Okay, maybe we shouldn't make this into this layer. What if we just were to do this? But it doesn't feel right either, does it? Let's try it at least. We are exploring new territories here, at least for me personally. Field name not in record of union initializer. No, we do need that additional layer, but why doesn't it work? Because this is the first thing in the array, right? This is the structure. Because if we were to just do one instruction, we would do instruction I is equal to dot O is move, dot A is, well, 0 and 5, and this will be the whole thing. But now we are doing several of those. So basically, instruction i's equal and shouldn't have this. And isn't this pretty much what we've done? Static program prog equals. What if we were to do, if we call this instruction instead? Will that make a difference? I'm not sure. I haven't really explored these new C functions, which is flexible initialization and stuff. Initialization of flexible array member in a nested context. Okay, now it's just complaining on this. Okay, well, I didn't remove the example, did I? Nope, I did not. But this seemed to be working until this point. And what is A? A is... can't that be it? This is undefined size, so we can't probably do it like this. That's right. Okay, makes sense. So let's do this differently. Yes. What do we need to do instead? We will still have a program. Prog. And a program will have several of these instructions, and it's the instruction that we need to allocate properly. So we could do the program as just an array of 2. And then we can do something like instruction I1 and I2. And I1 will be equal to, and we need to allocate for this, but how much do we need to allocate? Int size, no, int 16 size in order to figure that out, we need to use our instruction map, right? This tells us how big the different things are. So we need some kind of a function which returns the size. Let's call this, let's just call it map for now. And what it will take is the type of instruction. So in this case it's a move instruction. And then we have the size. So now we can declare this, initialize this thing. And this should be an instruction casted malloc call of the integer of size. And if we don't have one of those, we simply, no, let's keep the same structure. So we'll set the array number to mem, and we will return the program of 0. And then we will copy this whole thing and do it all once again. This time with a no-op instruction, and this will be I2, and now we have our two instructions. So I'm not sure if this is correct syntax, but let's try. Can we do program equals, and now it should just be equal to I1, I2. Might work. And then we will return our program. All right, something like that. Let's see what the GCC says. Okay, we don't have the map function. That is very, very true. Oh, so true. But that should be easy enough to remedy, right? So, the map function, it will return an int16 map, and it will take, what will it take? Let's remove this problem. Is it an instruction or is it an opcode? It's an opcode. So we have opcode O, or just opcode. And we need to create the function. So int16 map, it takes an opcode O, and we have int16 ret, and we need to search this map. So basically, let's see. Yeah, let's do this properly. let's create. We need a pointer to an IM. And we need the size of the IM, or the number of instructions. So let's say we have let's make it a constant to make things easier. So let's define IMs as the size of one IM, and an IM is a struct S in instr map. So this is one entry. And we need to take, let's see. We need to take the size of the entire instruction map. So size of instruction map, and we divide that by size of one of these. And then we should have the numbers, the number of, right? I think this is okay. And let's make it a one-liner so we don't have to do all of these backslashes and stuff. Okay, this makes this makes our lives a little bit easier. So let's define an int16 n and a ret, and we need an IM pointer. So we do a for loop where we set n equal to IMs. We set p equal to the first instruction map entry. We loop as long as n is not 0, and at each iteration we do n minus minus and p plus plus. And let's set the ret equal to 0, and at each iteration we check if p, and what's the name for it? We need to find the definition of the instruction map. Okay, so we have O and we have size. Maybe we should call this S instead. And that's an int 8. Okay. So if P O is equal to O, that's our argument, parameter to the function. If those are the same, we will set ret equal to P size and break, and at the end here we return ret. So it's either 0 if it fails or it has a number in it. I think this should work. We need to update our signature though, because we only need 8 bits. 8 bits ought to be enough for everyone, right? So now we have our map function. Let's see if it compiles. Almost. Prog OK, it didn't like this syntax. If I'm not entirely out and riding a bicycle, as we say in Sweden, in a proverb, I think we can do this JavaScript-like syntax, but I'm not sure. Let's see what happens. Nope, it didn't like that either. But I think one of these is okay, but only at declaration, which is pretty annoying, but we will have to do it like this. As you all know by now, I loathe declaring variables and giving them content of the same line, and I don't like at all to declare variables like this anywhere in the code, but I guess we kinda have to in this case, right? Let's try this first. I want to see if this works, or if I'm still riding that bicycle. Yes, I am trampling. But this should probably work fine, I guess. Incompatible types when initializing. Okay, that's probably because we need them to be pointers. Let's see. Who said coding your own virtual machine should be easy, right? We should expect to drive our heads into the wall sometimes. Another Swedish proverb, by the way. Okay, so registers, opcode. And the instruction is not a pointer, but since it contains this, we need the malloc for it. So instructions should be a pointer by default, I think. We make clean, jump down a little bit, clear the screen, we run make, and boom. Oh, yeah, even more errors. Type abstract, okay, I put the star wrong. It should be, yeah, where should it be? Struct as instruction, it should probably be here, right? Or maybe it doesn't matter, this looks better. So we make clean, we jump down a little bit, clear the screen, and boom. From incompatible pointer type, struct as instruction double star. Right, because now we don't need to do that anymore. since we are already dealing with pointers, where am I? Program pro is equal to this. Is this right? Let's see what happens. It seems a little bit weird. Initialization from incompatible pointer type, struct s instruction, double star, program prog equals I1. How did I define I1 and I2? I made those pointers there, that should not be right. Still it says struct double star. Okay. We need to change all this stuff at so many places. So this should not be a star there, and this shouldn't either. Okay, we're down to one screen. Excess elements in scalar initializer. X is okay, because we're defining this. Returning program, struct is instruction star from a function with income. Okay, the return type needs to be altered as well. So change this and this, and probably instruction. But it returns a program. I'm not sure actually. Let's try it this way, since it will be a pointer anyway. So just prog, and we call this and then we get from this. Let's see what it says now. First arrow will probably be there still. Yes. What is this? Line 18. VM. Okay. Maybe I should just search for all the stars and remove them entirely. This is getting a little bit tedious, to be honest. But that's programming. 52. Yes. And here as well. We're down to one screen again. Assignment instructions is a double star. So PP, where do we have PP? That's right. Let's search for all the programs and make sure have any stars anywhere. Okay, let's see what happens. Okay, this is something weird. Error too few arguments to function virtual machine. Right, we altered that signature, didn't we? We added the program size to it. But we have that right here. Maybe it's the call. Where do I call this virtual machine? It's not a main. So I need to define how many instructions it is, or what is the program size? Let's see. Sorry for my cat, it's going crazy. Let's see, program size. We use program size to allocate the whole program. Alright, so basically it should be the size of this example program. But this returns a pointer. Right? Yes, it returns this pointer. So we will not really be able to figure out that. But we can use our map. So let's do something like this. Int 8 size, and size will be equal to the map of move plus the map of no up. Let's add the unnecessary parentheses. And then when we call our new virtual machine, we send the size along for the ride. And let's compile this thing. And okay, this time it did compile, but we still got this annoying error. Or warning rather. Let's see, where do we, there it is. Format truncation. I thought I had that in the code. Let's see, search VM. Or where did I put it? I put it here. String up. Do I need to have this stuff inside of? That's weird. Shouldn't this take care of it? Ignored, blah blah blah. Let's see what happens if we put it inside of our other thing as well. So inside of here, somewhere, here maybe, and then we need this line, no, But it should not be push, it should be pop. Did I put in this pop thing here as well? No, it's a push, okay. So we save this, we save this, we save this, and we save this. So we do make clean, jump down a little bit, we clear the screen, and boom, it compiles, but we still got the warning, but I don't really want to deal with that right now. We did get this, and we do get a program, and we use it to create a virtual machine. Ladies and gentlemen, we have succeeded with today's task. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Alright guys, welcome back. Now I have gotten a night's sleep, and I have decided to change up a couple of things with our virtual machine, because I don't want to utilize the heap the way I have done it this far. So if we look at this instruction, for example, this is good in itself, but I'm not comfortable with how I used, let's see, the program. Where do we have the program data type? Maybe I should put these in alphabetical order or something. Let's see, we have iams, we have, maybe I can search for it. I like being able to find it without searching, but never mind. Alright, so at the moment we define program as a series of instructions. An instruction is basically a pointer to this structure. So I don't want it to be. Let's stop being a pointer. So we're gonna refactor our code, to use a new expression. The program is not gonna be, well, it's going to be a series of instruction in the end, so to speak, but at the abstraction layer I only want it to be a string of bytes, right? So basically a pointer to a program is just a pointer to a string of bytes, and then we can put our instructions in there manually using our copy function. I think that is a much cleaner solution. Plus, we will be able to utilize our own stack for that, or at least our own memory. That's one more thing I need to change. This here, the virtual machine has a stack in this case. Well, it's going to have a stack for sure, but I don't want this to be just a stack. I want this to be memory, because I'm going to divide this by a stack or a data segment and a text segment for the code. So in this instance, this will just be a memory. And when we have a memory, we can define a stack as a, let's let's define a memory pointer to be a stack. That's how I like it, I think. Yeah, let's keep it like that for now. We'll see if we do any additional changes. Alright, so now that we have a string of bytes instead of basically an array of instructions, we need to change a couple of things. So let's see. If we look at the map function, nothing is changed. The virtual machine, on the other hand, the program will be a pointer, which is basically just a string of bytes. Where did I put it? Program. Yes, string of bytes, int 8. So let's see, pp will also be how are we using pp at the moment? We are mallocing, right? Okay, so pp will also be a pointer, and let's search for either pp or what was the input value? Very difficult to see when it highlights this way. PR. So let's search for those two. We assert that we have a PR, and that makes sense. What's next? We allocate the program, which is just string, right? And we check that it's okay. And then we copy to the we copy the entire program, that's right. So we don't need to cast this. That is the only difference, I suppose. And that's all for this function. Then we have our example program, and this will be very different. So I actually think I'm going to delete the whole thing. Like so. And before we rewrite that one, I will make this pointer again. So let's search for prog. It will be the example program, and then we'll simply, Okay, so the only thing we need to completely rewrite is the example program thing, which now will return a string of bytes. So let's define this as a program, example program, and let's create, let's see, how do we do this in the best possible way? Maybe let's do it similar to how we did it before. We will create the instructions I1, I2, and instruction, let me find it in the code so we can look at it while we write it. Here it is. So an instruction is basically this structure then. an opcode and possible arguments. So let's also do, we need to know the size of these specific opcode instructions. So let's create an int16 S1 and S2 for the two sizes. And let's also create one argument. We have this args thing. Let's use it. So we'll create an args A1, A2. And we need to make those two pointers. Or actually we don't need the A2 because it doesn't have any arguments. But the first one does. And we also need to create the actual program that we're going to return. Let's call this prod. And let's start by allocating that. No, let's not, by the way. Let's start with the instructions. So the first instruction, I1, will be an instruction that we give to malloc. This will be an integer of size 1. And we'll do the same thing for size 2. So we need to first get those sizes. And that's pretty easy. We just call our map function and we supply the opcode. Move in this case, and in this case it's no op. Okay, so now we have room for these instructions. So let's set I1 and let's see the best way of doing that. Well, we could just do this, I suppose. So I1, or not write that. We need to do I1 and then O equals move. And what about the arguments? The arguments we do also need to allocate for. Or maybe we could just make this an array in this case. No, we need to know how big the arguments are. So let's make this dynamic. Sorry from the to and fro, but I have never coded anything like this before, so it's a little bit 2 steps forward and 1 step back. But you're learning same as I am right now, so I think it's a good approach. Okay, so move instruction. We need to figure out how big the argument is. So let's create another size variable, but this time it's gonna be the size of arguments. So SA1. And that's pretty simple to calculate since all our instructions is going to be 1 byte on its own, which means that SA will be equal to the S1 minus 1. So the rest of this thing is the arguments. Alright, so let's check if S1 is 0 or is not 0, and if it's not, we will proceed with allocating for the argument. So let's see, we will have an A1 which will be equal to the args of malloc, integer cast, and SA1. This should also be SA1. Okay, so now I have allocated space for the arguments. Let's also, by the way, zero out those things. So this will be cast to an int 8, and it's I1, and we want it to have a size of S1. So we can simply do this, and we do I2 and S2. Okay, now they are zeroed. I do also want to zero out this A1. Let's check that we do have an A1 though. And if we don't, we would like to, since this is an example program, let's just assert A1. And same here, before we do the zeroing, let's assert I1 and I2. We will not use this in production code, but it's good when we're doing these kind of example functions. Okay, so we insert this, and we zero out this thing. I don't think we need to cast this. And this is A1, and we have the size of SA1. Okay, so let's start with the argument. If you remember, we have the instruction, which is a byte long, and that will be the move EX part of it. So if you remember, this one means that it's a move instruction, and these other 3 bytes means that it's into the EX. And possibly that it's a number that we're going to give it as a second argument, and not another register or memory address or so. And then we have 2 more bytes of arguments. And all we want to give this is a 5, which will basically be, so it's move AX 05, right? So these 2 bytes need to be put inside of this arguments thing. Let's, by the way, assert, no, let's not do that. Let's see. In our case, we will have 2 bytes. The first byte being A1. So let's set A1 to 0. Or let's do it like this. And then we have A1 plus 1. And we will set this to 5. And this is our argument string. Okay, So now we're done with that. Now we'll do the instruction, and we have already allocated and zeroed that out, and we have actually already set it as well. So all we need to do now is copy this to our program. And did we allocate our program yet? I don't think so. No, because we did not know how big it should be. We do now, though, because we do have, let's see, we do have these S1 and S2, so we know the sizes of both. Right. So let's create, it's a lot of variables now, but I think it makes the code a little bit easier to understand. PS will be the program size. And the program size will simply be size 1 plus size 2. Easy enough. Program will be program. And we will malloc this. It's a lot of mallocs. Didn't I say I would not use malloc? We can use malloc, by the way, for these temporary arguments and our instructions, but the program I want to be on the stack, in the memory. How do we achieve that in a good way? Because we need to, well, we could give, no, this is a little problem. We use our function to create a virtual machine, right? Or a virtual machine needs a program as an argument. But we kind of need the other way around too. So they are dependent on each other. That's not really good. Maybe it makes sense to not give the program to the virtual machine constructor. Let it just create an empty program. And then we will have a specific function which will load the program into the virtual machine. That's better. Which means we do not need this pp. And what is this p? That's the virtual machine itself, alright. So let's comment this out for now. Like so. And I will also remove this pp thing. And I will not give a program or a program size to the virtual machine. So assert this should be removed. Size equals, this is the size of the virtual machine. We should zero the virtual machine, but that's where we can leave it. So we zero the virtual machine and we return it. So it's an empty virtual machine without any program. Okay, so if we do it this way, then to our example program we can give an argument of a VM. So VM, and let's update the signatures before we forget. This should be empty. And the example program should take a VM pointer. 2 steps forward, 1 step back, right? But I think this will be a good way, because if we give this example program a virtual machine as an argument, then we do not need this program thing, and we do not need the program. We do need the program size though, or maybe not. Yeah, we do, but we will not malloc this. We will simply use the stack basically, or the memory inside of the virtual machine. We need a pointer though to this program. So let's do a program P anyway, and let this P be equal to the VM's memory. Did we call it M or memory or what? S. Let's change it to M. So memory M, and memory is this 65K thing. All right. So we point this towards that, and this is where we will copy our stuff. So let's copy this first instruction and its arguments. So let's do a copy towards our P. Let's cast this to our P, which is pointing towards the how to call it, the top of the memory, I suppose, or the bottom, depending on how you watch it. And what are we going to copy? We are going to copy the instruction, which is I1, and I1 is always 1 byte, which makes this easy. Then we increase P, and we copy to the new P, next position. This time we take the arguments A1, and we need to cast this as well. This. And what's the size of the argument? That's SA1, right? Which means we're going to increase P by SA1. So now it's pointing to the next point of the stack. Okay, that's instruction number 1. The second will be much easier, since it's only the opcode basically. So let's see how we did this. We calculated this size, we allocate this. So basically all we need to do is we set I2 opcode we set to no op, and that's all we need to copy. So we copy into the new P, our I2, and 1 byte in size. And this is the whole thing. Now we can clean up a little bit all our mallocs. And what's that? We have I1, we have I2, we have possibly A1. Right, maybe we should check for that. So before we copy A1, in this case we will have an A1, but perhaps we will make this a bit generic later on. So if we have an A1, we will copy the A1, and afterwards we will free A1. And now we can just free I1, we can free I2, and then we can simply return our example program, which will just be, in this case, a pointer towards the top of the memory, in this case. So let's just return VM let's just return VMM. Am I doing this right? Yeah, I think so. It's a little bit disruptive, this function, because it modifies the virtual machine, but that's okay for now. Let's see what the compiler says about all this. We clean, we jump down, we clear, and we do make. Conflicting types, for example, program. Maybe I didn't update the signature enough. Example program takes a VM. Example program takes a VM. It should return program pointer though. Cast from pointer to integer of different size. This one. Cast from pointer to integer. But P is a pointer. I am casting it the wrong way. Okay. I should read the error messages more literally. Okay, so let's see, which one is it? Let's search for $I. Maybe we need to escape that dollar sign. This is right. Malloc I. Copy I. No, this should be 1 there. Do you have any more? Nope. Let's try this again. I2 is a pointer. Yes, I meant to do that. 84. So this should be an arrow instead. PS, let's remove that. Too few arguments to the example program, that's right. We did not update the function call. Okay, so we need to change up the order here. We can't create the virtual machine after the program. We need to do it the other way around now. So VM is a virtual machine, no arguments. We don't need the size, I don't think so. No. Let's see. VM equals virtual machine. This we can remove. Program will be equal to this, and we send our VM. PS. Because we don't really use PS anymore, right? No. Okay, now this should be fine, I guess. Make clean. We space down a little bit, clear the screen, run make, and boom! It compiles with an annoying warning. A1 may be used uninitialized. We copy from A1, but we do if A1. And where do we create this A1? Let's see. If we have an SA1. Okay, so if we don't have an SA1, we don't allocate for this. So maybe we should check for SA1 here instead. A1 may be used in it, but didn't we fix that? This is line 80. If SA1, we free A1. Okay, the compiler doesn't really seem to notice the difference. So let's use both just to shut it up, right? Still. Right. There should be something like this, which will just tell the compiler that I know what I'm doing, don't complain. And yeah, we can suppress the warnings, but we shouldn't really have to, right? But alright, let's move this to an own if statement. If A1, free A1. Simple enough for you, GCC. Make clean, jump down a little bit, clear the screen, we run make, and boom. Now what? Copy. Which line? 78. It's this copy. Still with this SA1 thing. Okay, let's do something like this instead. If S1, then we allocate. And then if A1, we do this. And we change this to A1. We move this free back into here. Imagine we are wasting several minutes of coding just to shut up the GCC for something that isn't really a problem in this case. Ugh, now what? A1, same thing. A1 equals 0. A1 equals 0. A1 equals, it's this one. How can that possibly be? A1 may be used uninitialized at line 67. And the line above, or 2 steps above, we assert that we have an A1. And this whole if statement makes sure we have an A1. So how can that possibly be used uninitialized? Am I missing something here? If S1, A1 is allocated, if A1, we do this. I don't really get it. I don't think this is a problem. And I am sick and tired of this error, or warning rather. So let's remove it. And do stuff like this on your own risk, perhaps not in production code, etc., etc., etc. But I just want it to be quiet. Okay, so which syntax is the right one? Is it the equal thing or this thing? Well, let's try it and find out. So we make clean, we jump down a little bit, clear the screen, run, make, and boom. There we go. We have a binary, ladies and gentlemen. Alright, does it crash everything when we run it? It does not. And it does give us a virtual machine, and it does give us its memory. Pretty good. Let's also, let's check if it its memory contains the right thing then. So I could write, and maybe I have one of those hex dump functions inside of birchutils. I think I do. Print hex, right? And it takes 3 arguments. What's the third? Print hex. Let's see. Where is it? Print hex. There. So it takes a string, makes sense. Its size also makes sense. A delimiter. Alright. That's pretty nice. So let's do print hex, and we give it a program, and we want to print how much. We have, well, basically we want to print this, right? Map move plus map no up. And what kind of delimiter do we wish? Space, I think. Or maybe just nothing. I don't know how to express that. 0 perhaps? And we will recompile this thing. And let's run it again. Birch VM. Okay, so this is our memory. So first, maybe we should have a delimiter. This was tricky to see. Alright, let's recompile and we'll try this again. Alright, so first we have a 1, then we have a 0. That's our move instruction. No, this is our move instruction. This is our argument, the number 5. And this is our no up. So it does exactly what we want it to. Okay. So what is the logical next step? Now that we can create a virtual machine and we can load a program into its... I remember one thing I do want to put in there. Because if we look at this thing, we have this, right? This is our virtual machine. And then we have our memory, which is 65K roughly of memory. So let's say this is it. We have a bunch of code here. So this would be our text section. Section text. This is our code. And we have some kind of graphical representation of our code. It's something like this. So this is our code. Then if we go to the bottom, we have section data or stack or heap or something, which will grow the other direction. And then we have this space in between. So this will be pretty static. When we have loaded our program, we know how much this stuff is. This can vary along the program session. So there's an imaginary line in between here, basically directly following this code and this space which is being used as the stack. So as soon as we have loaded our program, we want to set this break line, because then we can differentiate between different types of information. So we can, for example, limit this. So we can have plus read access, and we need execute, but we don't need write access. So we can make this read only. And the data section in turn will also have read. It will not have execute, because we don't want it to be executing code on the stack. It's a security risk. And we need it to be able to write and alter the data. And if we have this break line, we know the different types, and then we can put those restrictions in. So this break line will simply be an offset into the address of this last byte here on the program. So the memory is still this, but in addition we will have a break line. I'm not really liking putting this in addition to the memory. Doesn't really seem right. But let's do it for now. Maybe we can clean it up later. So basically, this will also be of the same data type. No, it will not actually. Let's just do this as an int 8 for now. So let's call this break for B. Or maybe we should make this some kind of integer, since it's an offset, right? So let's make this an int 16. That's appropriate. And let's call this B for break line. And when we have loaded our program, as we have inside of here, before we return this thing, what we'll do is we're going to set the VM's break line to be the size of our program, which is basically S1 argument size, or what did you call it? Size argument 1 and S2. That's our offset to the break line. Yeah. S1, SA1, S2. Maybe we need to cast this to be sure. This is a 16-bit variable. And let's double check that this is what it is. We have S1, S2, and SA1 right here. And that's just S1 minus 1. Yeah. Okay, now it looks right. Let's make sure it compiles. I didn't change much, so it shouldn't be a problem. And this should still run. No, it's seg faults. That's pretty interesting. It's seg faults. And all I did was adding these stuff. S1, SA1, S2. VMB equals this. Did I add anything else between the recompilation? Can this really do this? Yes, it can. Why? VMB. We're just setting a variable inside of the structure that we have pre-allocated. What am I not thinking about? S1, SA1, S2. S1, SA1, S2. All of these are in 16s, by the way, so I don't need this. But still, how is this possible? In 16b. Am I crazy or blind or something? I need to know what's happening in this. Is it the free call that crashes? Free I1, free I2. And we have pre-allocated both of those, right? I1, I2. We have asserted that we got them. Is it a double free, perhaps? We free A1 here. We free I1 here and I2. And why does this matter? I think we need to debug this more thoroughly. Let's open this in GDB. And before we do that, I need to copy a file. Let's go to Intel32 and cat my GDB. Okay, it's inside runlock. So we go to code, asm, runlock, and this. And let's create a file in my home, which we call B, and I paste this in. This is my settings to GDB. So let's cat this thing. Sup guys, welcome back everyone. So now I have moved my project to my 32-bit machine, so it will be a little bit easier to debug if we need to. And on this machine I'm running the absolutely latest GCC version as well, 14.2.0. And you probably need to compile that yourself if you want to run that version. You can download it from GNU, let's see, from gcc.gnu.org. So I want to update one thing. Instead of C2X, I can now do the real C23 standard. So let's save. And I have it. The new version does a couple of things differently. So when I mean the new GCC version. So when I run my make, I do get a couple of new errors. First, this one, that it's too large. I'm not really. Oh, okay, of course it is. So let's see, because where is it? Where are you? Okay, so I do have an unsigned int here. That's basically a 4.3 billion big thing. And I don't want that. No, I want this to be an int 16. So 65k. That's more like it. And I noticed another error. We are returning the memory address of this thing. And I was returning it this way because I thought, well, it's a pointer, right? But it's not really. It's a memory data type, and this is a char array, which is not necessarily the same thing. So I think we actually need to do this. Right. So if we save, what does the compiler tell us? Jump down a little bit and run make. Okay, we got rid of almost every error message. What's this then? Returning int blah 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 from a function with incompatible return type program star. Okay, so it doesn't like us returning the address of this thing when it's actually an array. It's probably still trying to, well, I think we need to cast this basically. And I hope the font size isn't too small. I reduced it one step so I could see all my code. But it should be all right, I hope. Otherwise, please let me know in the comments so I can fix it to the next one. Alright, so this is well, we want it to be a program star, right? So if we do this, okay, so now it works. And I'm still getting those warnings for truncation. I wonder why. It's because we should have eliminated those, right? Which reminds me, I forgot to load up. Let's go into the sociopath. I forgot to load up the birchutils, so let's do that. Because we probably is going to change stuff inside of there as well. So I will load birchutils. And I will drag this into my project. I love that we can do that. and then we'll close this one. So nifty. Okay, and let's double check this thing. We have the birchutils .h, and this, this is probably including the global thing. Why did I put it like that? Well, let's fix that. That's most definitely why we do still get those warnings, even though I suppress them. So let's see, we run make clean, jump down, run make. Ah, isn't it lovely? And can we run this thing? And it does not crash, ladies and gentlemen. That is pretty nifty, I think. And I wanted to double check one thing. Because we are allocating our VM instance, right? And I want to double check how big that thing is. So let's see. Close birchutils for now and the make file and this. Okay, so let's see. So inside of main, we create this virtual machine instance. Let's also do this equals a pointer. Let's say size like this, and then we'll simply do size of struct svm, right? And if this works correctly, let's see how much memory this should take. First we have a CPU, and what is a CPU? Let's see, where do we have it? Here. It's a structure with only one member, and that's the registers R. Registers R is a couple of registers. It's 1, 2, 3, 4, 5, 6, right? And how big is a register? It should be like 32-bit. Yeah, it's 16-bit, right? But let's double check so we know. So register singular, this is the one. Shorted, that is 16-bit. Okay, so we have 1, 2, 3, 4, 5, 6 times 2. That is 12 bytes for the CPU part. Then we have the memory, which is 65,536. So basically that plus 12. Maybe we shouldn't do this in the head, by the way. So let's see. We have 65,536 bytes plus 12. So this is the number we have this far. And then we have 1 int 16 for the break line. So we add 2. And then simply we have a pointer to a program. And a pointer is always, wait a second, pointer to program. How did we do that thing? Example program, print hex. And when we initialize that program, do we ever set this p thing. Don't think so. Because that should basically always point to the top or the bottom of the stack, basically. So is there really a point of having it? I don't think so. Let's remove this. Okay, so hopefully our memory will be this then, 65,550. 65,550. Okay. You can double check the same on your GCC version, because sometimes it has a little bit trouble with these kind of syntax, like when you type def an array with a predefined size. So double check that it does that all right, and that is probably by the way it works now in this version, and we had problems before, since it calculates that correctly and allocates enough memory. Okay, so now we can basically load an example program into our virtual machine, and that's it. What's the next logical step? Well, executing our program, right? So we need some kind of execute function. And what will that take? Let's see. So let's put that here, I think. First of all, what should it return? It should have like possibly a return value like main, you know, returns something at the end, but not necessarily. We can, for now at least, it will be a void, and it's called execute, and all we need to give it is a virtual machine and a program. Those two things. And I'm not 100% sure how I'm going to do with this program, because currently, since we did the refactoring, we are changing the virtual machine when we load the program. So basically, if we create a program with this example program, we are putting it inside of the virtual machine manually, so to speak. I think later on we will divide that stuff, but it's okay for now. It's only an example function, which means this should be the syntax. We could omit this, but let's have this for now. We're not going to be using it for a while, but let's do it anyway. No, let's not do anything that we are not currently using. It's better to add it later on. Okay, this is better. All we need is a virtual machine, and we can execute the instructions. And I remembered one thing. We need some kind of end instruction, because our instructions are basically a stream of bytes, and every instruction has a different length and so on, so we don't really know how long our program is, and that makes it troublesome. We could use the break line thing, because that's, let's see, where is it? This. Do you remember the break line between the stack and the text segment, the code segment in the virtual machine's memory? So this basically tells us where the code section ends. Not necessarily the same as the program. Currently it is, but not necessarily always. So I think I'd rather, at least for now, have an end instruction. Like in the good old days when you had a halt instruction, you know, that halted the CPU. I think it's still there, but yeah, not used very often in today's code. So let's take a look at our instructions. So here are our opcodes. Let's add one more, and this will be halt. Should it be 3 or 4? Well, we are never gonna execute two different instructions at the same time, except if we were to implement like concurrency and threads and stuff inside of our virtual machine in CPU cores. But even then we wouldn't use this kind of way to do it. So let's give this the number 3. And we also need to update our map, this one, and tell our system how big this instruction is, how many argument or how much argument. So this will be a single instruction, exactly like the no-op, and it will basically be this, right? 1 byte. Okay, so let's go to our execute instruction. And let's, by the way, no, let's do that later. Let's go to our execute instruction. And it's void execute, and it takes a virtual machine VM. And what does it do? We need a program pointer, which is let's call it PP. And let's double check, but a program is just a string still, right? We did a couple of to and fro's there. I need to find a better way to start looking for things. Instrument, VM, memory, program, yeah, intakes. Alright, so we can assert that we have a VM, and that the VM has a program loaded. And how do we check that? Well, we do have access to its memory, M. It's called M, right? Yes. And this memory is an array of bytes. So if we just check the first byte, if that is 0, we will quit. Because we don't have a 0 instruction. So this will always be 1 if we have loaded a program. Alright, and if we have, we can set the PP to that same address, VM. So to point to the first thing there. And then we will start parsing the instructions basically. So we will need some kind of a loop. Let's see how we do this. We will loop until pp. What are we going to check? If we hit the halt instruction, in that case, the current position of pp will be equal to how do we put this? Maybe we do this. Instruction. No, halt. Is that it? I've never used this kind of construct before with an enum. Well, instruction is a struct, so we need to go into the opcode O inside of there. So this should be instruction, this should be opcode, and yeah, opcode halt, because opcode is defined as the enum opcode, and we have the halt here. So I think we should be able to do this, right? It makes good sense. So if the current position is not equal to this, we will continue looping. And do we have another condition, by the way? I think we do, actually. I also want to check if, let's see, check that pp, the address of pp, is less than or equal to the break line, the VMB, because if we have gone past the break line, we are inside of the stack, and executing instructions from the stack is not something we want to do. In that case, we want to we want the program to crash. Or not our program, but our virtual machine's program should crash with a segmentation fault. So we can put this under here. So we do an if check of the same thing. If pp is less than, let's say in this case, if pp is bigger than the same VMB, then we should segfault, right? Segfault. And what does segfault do? Well, void segfault. Let's put the VM inside of here so we can clean up a little bit. Not that we need to, but so VM. And if we have a VM, then we free the VM. And what else should we do? Well, we want to print some error to the screen. stdr, or maybe we should just call this error. Then we can define segfault later on. So we'll have a VM and an error code. So error code, see, E. And then we can have like a switch statement of the value E, and if it's equal to seg v, I think it's usually done, but I want this in lowercase. In this case, we're going to print to the screen, to the error buffer, segmentation fault. And let's add VM in front of it so we can distinguish from regular seg faults in our code. Segmentation faults like so. Maybe even do this, just as a good habit, in order to make the code a little safer from format string bugs. And what shall we do more? For now, let's just break, and we have a default also break, and then we'll simply do exit -1, something like that. Okay, so now we got a new function as a bonus, and this is a void error, and we give this a VM star and an error code. What is an error code? We haven't defined that yet, but it will be, where do we have most of these? They are pretty spread out, so let's put it where we have several in a row, like here. So, and why would I want to do that? No reason really. I think it looks better. Okay, and let this be an unsigned jar error code, and we need to define the different error codes. Maybe its own section of defines here. So, or we have errors here already. Let's continue. No, okay, this is not the same. So define r seg, something like that. And this will be 2, and let's also put the binary in here, 0001 and 0010, and this we can move to its own thing. So r seg, and this should be okay. This should be r seg, like so. And let's also create a macro for that. Do we have any macro? Oh, right here. So define seg fault x, and if we encounter this, what are we going to do? Well, we are going to call error with the specified VM as an argument, and our seg, easy peasy. And that's basically what we did inside of execute, right? Seg fault VM. Nice. All right. So if we are still traveling inside of the text segment, the code segment of the memory, we will do something at each iteration. And pp will be equal to the first. Let's maybe, well, basically it will look something like instruction 1, argument 1, instruction 2, instruction 3. So this is in our case. And what instructions do we have? Well, we have a move to AX number 5, and let's see, how can we separate those in a clean way? Let's just, no, that's not right. Okay, let's do this for now. Second instruction, that was our no-op, and we will also add the halt at the end later on. And in binary, or in binary basically, we will have this 0, 1, which is the move AX, then a 0, and then 0, 5. This is our move, and directly following that we will have our other instruction, our no-op, and finally we will have a halt at the end. So this is basically our memory, and pp will point to this first thing. So the first thing we want to check is this thing something that has arguments, because we need to split up the instruction and the possible arguments. So let's say we have an args data type. So let's say we have A1 and we have A2, two possible arguments. And maybe we should zero initialize those. A1 equals 0, A2 equals 0, because they are pointers, right? And that's how we have used them this far, I suppose. Well, we do have it as an array here, but pointer is fine. So these are the arguments, and let's also create instruction. Maybe the instruction does contain the arguments, so we don't really need to define those ourselves. All we need is an instruction pointer, an IP. And that's not the register IP. Now I'm just talking about in our code, so to speak. Alright, so IP will be equal to the instruction casted pp. So it points to the same thing, but it will interpret it as an instruction. And we need a size variable. So let's create an int16 size. And size we get from the opcode we are currently pointing to, and the map function. And then we will know how much we should increase pp at the end, right? So when we are done with this instruction and its arguments, we will add that to the pp and go to the next iteration. But how will we use this? Well, basically we should just be able to do something like, let's say we have an exec instruction. So where we are now at the execute function, we are executing a program. But in here we are executing a single instruction, IP, and IP will contain all that we need. So basically the instruction opcode and its arguments, because they follow directly afterwards. And that's probably it, I suppose. Well, talking about instruction pointers, if we look at our registers, we haven't spent much time with those, but all these are 0 from the end, right? From the beginning. But now we kind of need to use some of them. So the stack pointer and the instruction pointer, we should actually have initialized. And where should we do that? For the time being, well, when you create our virtual machine, we don't need to do that, because then it should be 0, because we don't have a program, we don't have anything in the memory, and so on and so forth. But when we have loaded our example program, which we have pretty much down here, so here we set the break, but we should also set, let's see, VM CPU registers are IP. And what should it be equal to? Well, it should point to the first instruction, which is basically the register. Let's see. Well, it shouldn't point. We should actually put the address in there. So it should be the register version of the address of the memory, like so. But this is a little bit weird syntax. So let's see how we can do that better. Maybe we should create aliases for it. So macros, basically. Yeah, we should definitely do that. So let's create a couple of more of those dollar things. Let's define an AX, which will be, let's see, so we put the CPU in here, the virtual machine, and then we go to the CPU, we go to the registers in the CPU, and we go to the AX register. Can we do this? It looks kind of like weird syntax, but I don't really see why not. So let's see, how many do we have? 6 at the moment. So we have AX, we have BX, we have CX, we have DX. we have SP, and we have IP, and AX, BX, CX, DX, SP, and IP. Have you seen C code like this before? Huh? Alright, so let's see. Then we can change this to VM dollar IP is equal to this. Register of VMM. Okay, a lot easier, right? And what about the stack pointer? The stack pointer is always pointing towards the stack, and since we have not put anything on the stack, it will point to the beginning of the stack. And since the beginning of the stack is the end of the memory, it will have the last possible memory address. So VM stack pointer will be equal to a register with the last possible address, and that's always -1. Yeah. This should be it, I think. Which also means if we go to our execute function, where is it? Here. So when we are done executing the instruction, we do not only want to increase PP, we also want to increase the instruction pointer. So the VM's instruction pointer should be plus equal to size as well. All right, that's all good and well. Now maybe to the exec instruction we should also pass the VM, because otherwise it will be difficult to do stuff really. And how should the execute instruction function look? So let's see. Execute instruction, we take a VM, and we take an instruction I. Let's also create the signature before we forget. So we'll have a void execute instruction with VM star and what should be the other thing? We should have an instruction, a pointer to an instruction. Alright. Let's also create a no error definition. No error, which should simply be 0, 0, 0, 0, 0. Because when we get to the halt instruction, I want to exit using this thing. So basically I will run the arrow function with a 0 for convenience. Okay, so instruction, then we will have an opcode and all that, but let's start with the size. And it's not optimal that we need to recalculate this, but never mind for now. So we give this the I, O. instructions opcode, map that to a size, and basically we want to check if we have any arguments. So here it might make sense to have A1 and A2 as those, right? That's right. The argument size, will that always be the same? So for now, we do only have arguments to our to our move instruction. Where is our example program? Right here. So we set A1 to 0 and 0.5. So in this case, our argument 16 bits. Will it always be a 16-bit argument? Let's take a couple of examples. If we have XOR, it's going to be 16 bits, and same with all the other add and multiply and stuff. Int, same there. What else? We are also going to use compare and jump. Yeah, the instructions will always be 16 bytes. So how does this args thing look? Maybe we can define that in there. Okay, it's just a fixed size, a no size array. And args is just a string of bytes, I suppose. Where do we have args? Types of int args, yes, it's a string of bytes. But what's this first hit we got? No args. So I put zeros when we don't have arguments. That's not really what I want. Am I still doing that even after the refactor? Let's see. So the first instruction we put in the arguments. Then we have the second instruction, I2 somewhere. I2. Here we copy I2. Do we copy any zero arguments? No, we're not. And it's a bad idea to do it this way, because then we're wasting a lot of memory space for no real good reason. Well, it will be easier to code and perhaps less error prone while coding it, but no thanks. Alright, so these arguments will be 16 bit in size. So why don't we just make them 16-bit things, every of them? Why do we have to worry with those bytes and stuff? Because when we set those, how do we do that? In this case, we just do A1, this. And we could just have done A1, this, if we let it be a 16-bit thing. And I think that's how we're going to do it actually. So let's do A1 like this instead. And where do we copy A1? It's down here. So now A1 will be a reference to A1 instead, not the value. Let's see, where do we have A1 so we don't mess something up? Here we will just define it as A1 like this. A1, and then we don't need to malloc anything for it. If A1 is not necessary. But let's 0 initialize it at least. Assert A1, no. 0 A1, no, not like that. A1 equals 5. And maybe we should do it like this to make it extra certain that we are dealing with a 16-bit structure. Extra obvious, I mean. If A1, we don't need to do it, do we? Perhaps it doesn't matter. If we have an A1, we copy A1. And then we increase by SA1. What was SSA1? Size of A1, right? SA1 is the S1 minus 1. Yeah, we don't really need to do it that way, but it's okay. Right. And then we will simply define arguments A. It can be several, which means we can leave this as is, and this we will change to 16. Right, let's compile and see. We will probably get errors because we're in the middle of creating our function, but I just want to see if this part works after we have cleaned up some of the errors. In 16 size, not used, unused variable, blah blah blah. Warning, comparison between pointer and integer. If pp is less than or equal to the VMB. But shouldn't we be allowed to compare those things, right? It's just an address. Maybe we can cast it somehow to make sure that we remove that warning. Okay, and this we need to change on line 28. And an expansion VM.IP. So the virtual machines, C, and this. And how does it look? If we look inside of here, what do we have? We have a VM, and then we have the CPU C. And if we go to what a CPU is, It's a structure that looks like this. And this has an R, which is not a pointer. That is right. So let's see. VM is a pointer. This would be like that. C is what actually? Is C a pointer? No, that's not a pointer. And neither is R. Which means, let's see if we can do, no, we cannot do that. My short, what's the name? Short keys, short commands isn't really configured the way I want it to be. This should be able to make this bigger, right? But it's impossible with this keyboard. Let's do some sed magic or Vim motion magic. So let's see, what are we going to change? We are going to change the string to C to R to something into to C dot R dot something. Right. And what else? We had one more arrow that I mentioned. Not those. Not this. Right, 28. In the right file, perhaps. 28. This is right. Should be a pointer. And can we cast this comparison somehow? Let's see. PP is a program pointer, and this is a memory pointer, perhaps? No, it's just an int16. So let's call this a program star for now. Can we do this? I'm not entirely sure. Okay, let's see. Wait a second. I just had an epiphany. No, because it is the actual value that we want to compare, not its address. Since the value is an address, right? So we make clean, jump down a little bit, we clear the screen, we run make, and boom. A couple of warnings, blah blah blah. Cast to pointer from integer of different size. Is it really? PP, well, it's an int 8. But we're still only interested in its value, so maybe we shouldn't worry too much about those. Statement with no effect, an expansion of rsegv. Okay, well, it will have effect when we're done with this thing. Okay, it didn't like this. rsegv define. Right, we cannot name it. Wait a second. Right, we need to have a keyword in front of it. That is correct. We need to have the case. Okay, warning. Free A1. Yes, that is a little bit hard to do when it's not pointer. So let's see, where do we free that thing? Probably inside of this free, this it is. We're done to one page, more or less. And what is this? Register undeclared. Right, it should be just reg. This is up here somewhere, I think. No. Register. Here it is. So this should just be reg and reg. And let's see, cast from pointer to integer of different size. Well, that's not really a problem in this case. Shouldn't be, at least, unless C is interpreting my code otherwise than I am. And this one, maybe we should cast that one at least to make it more clear what we want to achieve with this. Because this should be treated as it were a pointer to the program. Well, either that or we cast both as memory, but that we can't do that since memory is always a specific size. So no, can't do that. I think we will leave it like this for now. I don't care too much about the warnings. I even think for the time being, since we get so many warnings that's not even relevant to our code, I will actually change my makefile and remove wall. And O2 should be enough. Okay, I'm in the wrong makefile. That's a little lame. Okay, like this and this. So quit, it should be this makefile, right? So O2 is okay, but remove the wall for now. Do we still get warnings if we do like this? Let's see, we make clean, we're down a little bit, we clear the screen, we run make, and boom. Okay, still a couple of them. I don't like these warnings. And this is not really a good practice, suppressing warnings and stuff like that. But since I know what I'm doing, what is it called? Dangerous statement to do. If I do make an error later on. So let's see. There is an this kind of sign here, a dash. It's not a dash by those other ones. Should I remove that? No. Winter pointer, W pointer. This is something else. And if our program crashes now, then at least we know that, okay, those warnings were correct. But I can't see them being correct, actually. I have a hard time seeing them being correct. Wind pointer casts. Let's do this again. I was thinking of something else, and that's never good. So let's remove this, and we do paste, paste, paste. Winter pointer cast. That's exactly what we want to remove, right? And we have that here already, which means pointer, winter pointer. And what was the last one? Is that what we have in our copy paste buffer? Let's see. W pointer and wind pointer. W pointer. We do have this though. But let's paste this in. It's exactly the same. And all of those don't have this dash. Let's try this and see what happens. Unknown option after blah blah blah. GCC diagnostic ignored. W, which one is it? Dash, the one with the dash. This. So if we were to remove the dash, will it work? No, don't think so. Maybe we shouldn't have the whole thing. Maybe we should just, I don't really remember how it's done. Lord. Maybe it's just like this. This looks really weird though. This should be the right thing. Let's save and try this. Move down, make, no, that's not it. Okay, put those back like so, and we run make again. We get a little less, but still we get this warning. So let's copy this specifically and see what we are missing. So wind to pointer cast. Wind to pointer cast. Right. We should probably just have this, right? And now it should be nice and good looking. Yeah, that's how I like this. And no crash. Pretty nice. Alright, let's see if we can finish this execute function, and then it will probably be it for today. Let's see, where are we? We are executing this inside of here. Okay, so we have calculated the size, and these shouldn't be pointers any longer. We can still have A2 though. And let's initialize them. Did you know that you could do this, by the way? A1 equals A2 equals 0, and everything will be 0. One neat little trick. Okie dokes. So let's see. We have a couple of different possibilities at this point. Let's do a switch on the size. We have K0. Then we just break. We have case 1. Then we have one argument. Let's set A1 to what exactly? Well, A1 will be the first in the array. So basically it will be I A for arguments 0. Right? And we break, and if we have case 2, we will set A1 to OA 0. We will set A2 to OA1. Break. And if we have something else, then it will have gone terribly wrong. And in that case, we will segfault. Okay. So these are different things. And now when we have these defined, we can switch for the opcode. So we switch for O, I, O. And if you don't understand what these are, I is the instruction here, right? And an instruction contains an opcode, which is named O. So that's basically it. And if we switch for that, we should be able to put something like, I have never done this with enum, but logic dictates that this would be possible, right? And if we have a move instruction, we will call move, and we will give it, and should we have different kind of moves? Yeah, the opcode will tell that. So we give the VM, we give the instruction opcode, and we give the two possible arguments, A1, A2. Then we break. We can also have a case for no op. in which case we does nothing. And then we have a case for halt. And then we will simply do something like we'll do error yeah. Or maybe we should have its own for this. It's not really an error, but let's call this system halted without error just to show that. Using the error function is good though, because that exits everything. And this shouldn't return anything. So let's go to the error function and add our case, which will be case, what did I call it? Sys halted. At which point we will simply write something to the buffer. System halted dot. No dot. And then we break and exit -1. Maybe we should create an exit code. We only need an int8 for this. Exit code. And let's set exit code to -1, but with the possibility of changing it, like in this case, where we'll set the exit code to a clean 0. Oh, what happened there? There we go. And we will exit with the int version of our exit code. Okay, so we have new functions, don't we? Well, we will have a new function, which is move, which takes 1, 2, 3, 4 arguments. And there will be a lot of those functions. So maybe we should put our own section here. Okay, so void move, and it will take a vm star. It will take an instruction. No, not an instruction, an opcode. And it will take args. Maybe we shouldn't have that in plural, but whatever. Okay. And what should the move instruction do? Well, it can do a whole lot of different things, but at the moment we can only move into a value into a register, which makes it a little bit easier. So let's see, void move. Maybe we shouldn't have void because never mind. If we need to return something, we will put it inside of a register like it's used. Okay, so let's see. We have vm star, vm, and we have the opcode. We have args a1 and args a2. possibly. And what are we going to do at this point? Well, the only thing is we're going to update the VMs. Well, we'll simply do this. The VM's AX register should be equal to the reg A1. And that's it. So if we run this program, let's see, we should be able to check what the AX is. And this should be, let's see, 4 digits, 16-bit X value, and it will be this VM's AX register in an integer format. Okay, we make clean, we're done a little bit, we'll make okay, that's a red error. Void move redeclared as a different kind of symbol. Okay, so we can't name something from an enum into that. Okay, so how should we name them instead? I want basically the same structure for all my instruction functions. Let's see. Let's put I don't really like those things, but let's do that in this case. 2 underscores in front of move. And where do we call move? Let's see. Did I miss it? Where do I call this move? Well, switch, right here. Okay, and we also need to change it here. Just so we have some kind of symbol to differentiate those functions, because there will be a lot of those probably. So we make clean, we move down, we run this, and boom, it's red still. Void move. Didn't I change it? I believe I changed it. Yes. And I'm not disconnected either. Well, let's add a space here, we save, we remove the space, we save, and let's make clean, go down a little bit, clear the screen, run make, and boom. Okay, less errors at least. Size of array memory is too large. What the fuck? Oh, sorry for the foul language. But it's like we're moving back in time. What is happening? This is like my code from before, right? It's like I'm reliving the same memories again and again, like Groundhog Day. Okay, now it worked. Weird. Very weird. Maybe some buffer or something in the SCP client got lagged up or something. Well. O is undeclared, is it? A1 is equal to OA. The argument of should be IA, right? Oh. This looks weird. This should be it should be the instruction. And then A is the argument. So this should just be IA. IA like this. Okay, so run the clean, we'll jump down, we'll make and boom. Okay, still errors. Sysholt undeclared. Yes, it is. This is actually a sensible thing. Alright. So let's see. We have our mem, we have our this and our that, but maybe we increase those a little bit. So this will be 1, 0, and this will be 1, 0. And let's put our sysholt up here, so we differentiate it a little bit from the actual errors. Zero, 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 1. Okay, now it might actually work. We run it clean and do all the other stuff. Make, boom. No, still not. Error sysholt too few arguments. Too few arguments to error. What could we possibly want to give that function? An error code and a VM. Who would have thought? Who would have thought? Who would have thought? Who would have thought? Okay, so let's see. Sysholt. We should put in the VM here, right? And that's basically it, I guess. Let's see what happens. Okay, one more. And that's just, oh, I love these errors. It's so easy to fix without having to put much thought into it. So save this, and now I can for certain say that we run make clean, we jump down a little bit, we clear the screen, run make, and boom, it compiled. It's compiled, ladies and gentlemen. Does it run without crashing, etc., etc.? Yes, it does. It does. It does. But AX is 0. Why is AX 0? Why is AX 0? Because, let's see, we'll create the virtual machine, we'll run the program. No, we don't. We don't run the program. We just create the example program. Let's execute it as well. So we'll just execute. And what's the argument? I think we need the VM. And that's, I suppose. Execute, execute, execute. Yes, just a VM. Okay, so will it work this time? Let's see. No, no, it's segfault. Boo. But that is not so entirely wrong though, because we don't have a halt instruction in our program. We do not have a halt instruction in our program. I think the break line should, well, what kind of segfault was it? It's a VM segmentation fault. That's correct. Yes, it should be crashing, right? Because we don't have a halt instruction. So now it was trying to execute on the stack, instructions on the stack, and that's not allowed. So it's segfaulted. Ha, cool. Then it works exactly as it should be. Perfect, perfect, perfect. Okay, let's see. We will add a third instruction here. Okay, let's just size. This is the instruction. I3. Well, there we go. Okay. So let's see, we will allocate for this will also be of size 2. Why is this happening? AB, let's see, S2. The size will be the same as S2 basically, but this will be our I3 with 0, I3 with S2, and then let's see. Right here we are copying. Yes, so we need something like this at the end. But this will be I3 and it should be a halt instruction. And we copy to P. We also need to increase P. We copy to P. Our third instruction. Okay, now we have a program I think we can run. A VM segmentation fault, isn't that beautiful? Our own VM segfaulted, and our own VM is still segfaulting because we are not updating correctly. Are we? let's see the executes. Let's first see that it really updated, because I think we had problems with that before. So let's see, we changed the example program function. We increase P, set the thing to halt, and we write to P this instruction size 1. We update, let's see, instruction pointer will point to the first instruction. Yeah, that's right. But when we have run an instruction, are we going to update it in here or maybe in here? So we execute the instruction and we update an instruction pointer. So that should not be the problem. And the size is also correct. If P, okay, so maybe this is actually wrong. Maybe the wording was correct. But PP is a pointer with, and the pointer has an address. Yeah, I want to compare that address to the value of this VMB thing. Maybe we should not cast this to maybe we should not cast it to a pointer. Maybe we should just cast this to an int16. And then we cast this to an int16. What happens then? And we need to do the same over here. It's always difficult when dealing with these kind of pointer, these kind of things relating to pointers. The only way, now it can give this error for 2 reasons at the moment. It can be this, that this is true, so that the current PP, well, it's increasing right here. So it will always, at the end, be a couple of more, no, one more than the break. What did we set the break to, by the way? We set it to, I'm not sure. Where did we set it? Let's search for B. There's one. VMB equals the first size, its argument, the second size. We should also add the third right here, but I'm not sure. Maybe this is the problem actually, but I don't think so. Instr. S3, right? S3 is the same as S2. So let's just put this like this. It's not very good looking, but this is just an example function, so we don't have to care so much. No, that's not it. But it can also be the other one. Let's see, seg fault. This case, when we execute an instruction which has a size which is not 0, not 1, and not 2. But that's not really it. Must be this other case. Annoying, how do we compare the pointer's addresses? Or one pointer's address and one value. Maybe we need to specify that this is actually the reference we are comparing, and this on the right here is the value. Still not. Well, this is just a security feature. We can remove this for now. I will have it in the end code, but it's not really that important for now. So let's see, remove this, but we save it. And in this version, we only need first thing here. No, that's too much. It's too much. Okay, so the only thing we check is that the program pointer is not equal to the halt instruction. Okay, now it should not be able to seg fault. Okay, it loops. Probably it never finds that halt instruction. But it should be there, right? We can double check easily by going to the main, temporarily removing the execute here, and looking at the stack, or not the stack. We're looking at, wait a second, plus of halt. Well, the memory, how would memory looks. Let's see this. Okay, so we have move 5 into AX. Then we have this, which is no up. And this is the halt. So we do have a halt, which should halt the program, and it should not be an endless loop. But it is. It is. So let's see. Where is our execute? And we have program pointer pp begins at the first memory address, and it should increase by this size every time. But maybe, wait a second. No, that's not it either. But I think this is a better way, actually. So let's run while. No, not while. Let's run do, and then we'll do while. While what? While pp is not equal to the opcode of halt. Will this make a difference? Well, currently it will not make a difference because we're not even calling the function, but now. Still an endless loop. What if we were to trace this thing and see if it gives us any information? Just have to write this out. What about ltrace? No. Let's go into this execute function. Because a pp is a program pointer, and it's what is a program? That's only an alias for an int 8, right? Yes, int 8. So it should go through this VM thing. VM memory. And it's not something like this, but I don't think that would matter in this case. If it don't matter, why does it even care about it? This is a memory. Oh, same thing. I think we need to add some debug messages. But let's see. Assert VM and VMM. Building a program VMM. The current instruction is equal to the instruction of PP. Is it something like IP is equal to? Do we need to dereference this? But maybe. Yeah, actually, that could be it. Okay, now we get an actual segfault. IP is equal to the instruction this is currently pointing to, and instruction is a structure isn't it? I have so many types. Yes, it's a structure. So doing this is not really sane. What if I were to do this instead? So instead of pointing towards this, I will copy it into IP. I will copy the contents of PP at that position. And 1 byte, because I only want to read what the opcode is. So we can remove this. Right. This should work, right? And we update the instruction pointer and this pointer too. Let's cast this as well. Right. What happens this time? Now what? 66. Size equals map IP. Okay, it's not any longer a pointer. Makes sense. VM and IP. And in this case, we should probably send. Never mind. This is probably okay. Okay, it's not. Let's send the reference. Let's send the reference. And we're back to square one. Why is this happening? Let's print some stuff. Anything we can think of. Size is equal to something, and size is this. And then we will simply do all these other things as well. What is PP? That is an address. No, it's a pointer. And it's called PP. What else do we have? We have this IP thing. So let's. Well, we're only interested in one thing, and that's the IPO. That's all we have here. And for the sake of everything, let's just flush this as well. And we run make. Okay, let's scroll to the beginning. Too far. Let's do more. Ahead. Okay. So VM is equal to this. Our program is equal to this. PP points to this address. Size is 0 from the beginning. What is IP? Strange number. pp is equal to the program of the address of VM memory, but the address of, yes, I guess. What if we did this? Would that make a difference? Because VMM is an array let's just test this out. Still, it's very weird. Because at this point we should have something in the memory, right? Because we have read in the program, and down here we can actually read from the memory. Because that's what we're doing right here. And this is a program. Same as here. And the program is this, which is this. And the virtual machine is allocated on the heap, right? So that shouldn't be the problem. And we return the program of VMM. Here we use a reference, but we tried both ways. Because pp is equal to the program of VM. And we have already asserted that VMM does contain something. And from that we copy it into the IP. Maybe it's different size. Yes, an open code is 16 bits, isn't it? Type def enum opcode. Well, that's not really clear. But it's probably 1 byte. So opcode is 1 byte, pp goes through byte by byte. And we copy 1 byte into the IP. Maybe we can even do IPO. Maybe that's it, but it should be the same because that is the top of the structure. But you never know, maybe GCC does some optimizations or whatever. Nope. If we dereference pp, what do we get? If we dereference, where is it? Execute. Let's change this to this, and instead of P, let's do 2, and we want this to be 8 bits, so double H and X. Something like that. So pp is equal to 1. Why can't we exchange that 1 for a size? We have done that before. Because size is equal to the IP.O. And pp is equal to Would it make it? No, it shouldn't. Maybe it's something special with enums. What if we were to do IP.O is equal to pp? Would that make a difference? I'm still running out of ideas here. Okay, now it works. Okay, so that's something, no, still crashes, but now it at least doesn't go on forever. But it has a VM segmentation fault pretty early on. And the only thing that can cause that, well, almost nothing can cause that at this point. Only that the size is something else than 0, 1, 2, right? What's up, guys? Welcome back. I think I have figured it out, finally, why this is crashing and behaving erratically. If we look at our virtual machine structure and the memory more specifically, the memory is a 65K buffer, and the lower addresses is the code segment, the text segment, and the higher addresses of the stack, which we haven't utilized yet. Then we have the break line in between. But what is this? It's an address, yes, but what kind of address? It's not a memory address in the C program kind of way, like the process's general sense of memory. This is more like an offset inside of this. So it is a valid memory address for our virtual machine, inside our virtual machine, because that's how our addresses look. There are 16 bits. But in this sense, this should be an offset into this, which means that if we want to use this like we are using it right here, no, where is it? Right, like we did here before. Let's put this back. And let's make this a general kind of, what word am I looking for? A general kind of, never mind. Okay, so let's see. In CCMP, we compare it to the VMB. But instead of VMB, we should compare it to let's call it break address. And where else do we have this thing? So let's go and search for, let's see, it's virtual machine and the break. Okay, so here as well, this should be the break address. And then we are here. So here we see, this is just a couple of 1 and 2 and such like that. So this break variable might contain like a 6 or something like that. We can't use that as a memory address on its own inside of our general program, so to speak. No, we need to add a prefix. So let's see, what we need is a program pointer. Let's call this, oh, we had a name for it, right? Let's see. It should not be a pointer, should it? It should just be an int16 break. What did we call it? Break address, right? And what is the break address? Well, the break address, the break address is the memory of our virtual machine plus the break. So this is what we should have done from the beginning. Now we can remove this stuff. And copy this IP. Oh, we can do it both ways, I guess. Let's do this a little bit more optimized, I guess. Size equals map, blah, 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 blah. Okay. So we run make clean, jump down a little bit, clear the screen, and right. And do make. Boom. Okay, error. Assignment makes integer. Okay, same thing. Not the same thing, but the same error that we got before and got rid of. Because let's see, which one is the problem? VMB is just an integer. It's this one. So we run make clean, jump down a little bit, clear the screen, run make, and boom, it compiles. Let's see if it runs. We still get a VM segmentation fault, but that might be, let's see. Let me see how many iterations this loop does. I think it does more than it did before, because before it didn't really do any, or one perhaps. So let's print a dot at each iteration. 0. Let's see, we're comparing the address of the pointer. Maybe we should do this. Okay, now I have 1 dot. So we might have a little bit of an off by 1 situation, I suppose. Let's type this out. At least we are farther than we ever were before. But let's see. In the first iteration, pp will point at the 0, 1, ex, move to ex, or ax, I mean. And at this point, the break address will be a constant. It consists of the sizes of all the other instructions. And what do we have? We have 0, 1, and then we have the thing we are moving, which is 0, 0, 0, 0, 5. And we have 2 more instructions, which means that the break will be 5 and break address will be the memory address of this right here. And what will the address of pp be? Well, first it will be this, basically this whole thing at the first iteration. Then we will plus it by 2 bytes. So if it points here, it will 3 bytes, right? So 1, 2, 3. Okay, now it's pointing here. And the break address is here. Wouldn't that mean, let's see, pp, let's do it like this instead. So x is pointing towards 1, 2, 3. It's pointing towards the third. And the brk is pointing towards plus. So it's this, and 1, 2, 3, 4, 5. So pp is 3, and this means less than or equal to this. Something is still not right. Let's print the values then. pp is equal to 0xx. Or maybe we should just take a pointer here and we do pp, and then we print f brk, this we will do 0x percent point 08x or not. By the way, just do percent $x. And here we'll take the value of BRK address as an integer. And what will be the result? Let's also do this, just to separate it a little bit. Alright, what do we get? So, let's see, the PP is pointing towards this address. This looks very weird. Yes, we do need a new line here. So the PP is pointing towards this address, and the BRK, okay, the variable that we created is only 16 bits, and the address is on a global system is 32 in this case. So what we need to do is we need to make, let's see, we need to make this a 32-bit thing. And instead of doing int 16 right here, we will do int 32. And this we don't need to cast at all. And same here. This should be int 32, and this should be as is. And now, ladies and gentlemen, I believe our program is going to work. I can feel it in my toes. Okay, it didn't. No, it didn't run. It didn't do any iteration this time. Maybe we should take this and put it here as well. PP and BRK address. Okay, so this is the address, and BRK is still a 16-bit thing. Why? Why, oh why? Because of this, of course. Okay, let's do it again. Okay, let's see. So we have this address. This is the PP, and the break is this. They are pretty similar all the way, but this is a tiny bit bigger. It's quite a lot bigger. Too much. Let's check the difference. No? Okay. So 7. And then we have the next one. So this is the starting point. And this is the same, I guess. And then the loop exits. Okay, let's see. Let's make one of these at the end too. So this is just before the next iteration. So AC and B3, and it's AC and B3, so it's the same. It doesn't change from, wait a second, we have it before the loop, right? Which means, so this is what happens before we get to the loop. AC and B3. This is happening inside the loop. Okay, so it's exiting here somewhere. It must be inside of the exit instruction. And that can only be because this size fails. And why does the size fail? Because it's not able to grab the IPO. Let's also print out the PP. And let's print both of these as a 1-byte hexadecimal number. What happened now? This is really weird. This should be PP. And let's make this like so. Or no. I guess this is right. No. Let's leave it for now. Alright, now we get a little bit more information. If we manage to put a semicolon correctly. Okay, so the PP is 1, the IPO is 1. Still fails. Which can only mean that the size is failing, right? So let's check that as well. Wait, this is not right. Don't think that would have made a difference though. And this should be the size. Let's add a new line as well. The size is 3. Still we get this segmentation fault. And we get it. It must be coming from the exec instruction. And what are we sending to this? We're sending the reference of the instruction on the virtual machine. What is the definition of this function? VM instruction star. Okay. And what does it do? It let's see. It takes the size, so it does another map call. That's not very optimized, but never mind. And it should be able to grab the size that way. But is it? What if we were to cheat a little bit and use one of the new C features, so we can send the entire contents of a structure as a value to function? So no pointers at this point. And we switch on the I.O. First off, does this make a difference? So in this case, in order to call this function, where does it happen? Here somewhere. There. So now we send the value of this structure instead of the reference. Okay, now what? Right. That makes the signature slightly different. We which means we need to update our .h file. Exec instruction, remove the star. Forgot one, and that is on 36. So this should also just be a dot. Let's see if this made a difference. I don't think it should, but who knows? IPO is 1, size is 3, exit. So this IO thing, .0 x I.O, and let's also check the size, same as we do at the other end, but we need to know if this is not transported correctly. So we'll do something like that. And we have an IO of 1 and a size of 3. So it's not that causes this thing. And we are switching on the size. And the size was, what was it? The size was 3. We check for 1 and 2 and 0. For 1 and 2 and 0. We should remove this and check for let's see, it can be 1 or 2 or 3. Let's see, if it's 2, this is what we do. If it's 3, this is, and let's keep 0 and 1 as well, or not 0, but 1 should be kept. Okay, I feel confident now. I can remove all the printfs. Annoying little thing, right? But that's coding. So we can remove all of this, all of this. This can go in this and this, all of this. And let's run, make clean, move down a little bit, clear the screen, run, make, and boom. Okay, it's still safe, but it's not the same thing. Now I think the off by 1 situation is occurring, which is a little bit more anticipated. So let's see what happens here. So AF B3, B0, B3. So we go from AF to B0. That's 1 increase. And then it will increase by 1 as well. I have too many of those now. This is no longer interesting. This is no longer interesting. And not this either. At the end of it, it's interesting. And we have AF B3, B0, B3. So this is the state when it decides not to loop anymore. But this is still lower. And this, right? What about this? If PP is not equal to opcode halt. So if it's equal to opcode halt, we should still run this one more time. Okay. So let's move this thing down here. Let's just do as we did before and put a do here. And this basically means that we are going to run this no matter what and then check the condition. And that is probably what we need, I think. So AF B3, B0 B3, and then segfault. I need one more thing. Let's put in some kind of separator thing here, so we know when it starts. Maybe I should call this a course of troubleshooting instead. Okay, so here it starts, here it ends, and then it ends. I don't want to have this as a condition. Let's just make an if statement that handles that part. And we already have one. And where should we put it? As soon as we tries to execute an instruction. So, no, not there. Well, doesn't matter, we can have it here. This should go. So if this memory address is less than, if this memory address is more than the BRK, then we segfault. Otherwise we do all this stuff and we loop as long as we have this thing at the bottom. So this mixing up or changing up of the while loop doesn't do much. PP equals to size. Can't we have that in the beginning instead? But I don't want that to happen the first iteration. I can do this though. And set size to 0. It's already 0 perhaps, no. Size equals to 0. So at the first iteration we will not add anything to this. Then we do this and we check this and this and this and this. And we update the instruction pointer. Maybe we should do that at the same time. And we update size as soon as we have read an instruction. Okay, this makes sense, I think. I must have missed some kind of, yeah. Did the function really end here? Oh, can't remember. But I can Control Z and I can go back. Yeah, it kinda did. So let's just put something new. Like return, and then this. And what is this function? It's the execute, right? Yeah. Alright, this should do it. And fingers crossed. VM segmentation fault. We didn't get any print this time. Not even this. Yeah, we didn't get that. So this happens, and this IP is equal to PP, and if this PP, maybe we shouldn't have this. That could actually be the thing. Yeah, here we go. All right. Sometimes it's a little bit tricky with all of those pointers and stuff. So, okay, let's clean this up a little bit. We don't need this, or this, or this, or this. And what do we print? We run execute, and then we want to print AX. Let's just copy this, delete it, and then we will put it in manually somewhere just temporarily so we can see what's really going on. Perhaps inside of the error, because we are doing this system hold kind of thing. So why not use it for displaying the contents of our AX register. And if this is 5, I am celebrating with champagne. No. No. It's different each time, which suggests that it hasn't been altered. And we are going into the VM and doing its AX register. But we are executing this move and going into the VM. We're setting the AX to argument A1. And this is a 16-bit thing. This is, how big is an argument? I have moved it around a couple of times. Arguments. We are so close now. Okay, an args is int 16. We're calling move. Must be from this exit instruction. We're calling move by the VM, the opcode A1 and A2. And A1 and A2 are set to 0, 1, and 0, or 0 and 1 in this IA. So inside of the instruction there is an argument, and we are using them like this. And we only have one argument. No, we have two. Let's see, our instruction is 1, and then we have one additional argument, which is a 16-bit thing. So it will still return 3 bytes. A1 is equal to A2 is equal to 0. That's interesting. We are 0 initializing them, which means it is set, but it's set wrong. So the argument is not pointing to the right place. And where do we copy the arguments? Let's see. Right, we are only, we changed this. Okay, so what we should do after we have gotten the size is we should copy to the IP as a string of bytes. We should copy from PP size. That should be it, right? And we don't need to set this like so. In this case, we can just refer to it like this. As long as we tell that it should be an instruction or an opcode perhaps. Yeah, code. Alright, let's try this again. So we make clean, we jump down a little bit, we clear the screen and we run it like so. And now I messed it up again. PBRK, this hasn't changed. The size we get from this. Weird. What if we keep this? Does it make a difference? No. What did we change that could cause this to happen again? If pp is not equal to opcode, by the way, I don't think we should compare the pp. A better way would actually be to let's see, to compare IP, to compare the value of IP and BRK directly. So if the instruction pointer is more than the VM's break, then we should segfault. But I don't think this would make much difference in this sense. So size will be 3, so we copy 3 bytes from our byte stream. We execute that. We check that it's not a halt. We increase by size. Set this again. Do the check. I'm not even sure what I did that could mess this up again. We were almost done, right? And this should be the VM's instruction pointer. still does this. We only see the rights here, and here we see the rights and nothing more. What did I change? The only thing is I use this to copy stuff, but is that really something that will affect this in this kind of way? No. So what else did I do? What else did I do? Okay, so let's Control Z until we get this to run again. Okay, so this version, okay, it's in the same. And this annoying caps lock, I hate it. Okay, let's see. Okay, so this version should run. System halted. So why does the change I did mess that up? Is it possible to... Yes, let's see. Okay, so we have this printf that won't change anything. Then what? I add this copy step, but that didn't seem to be the thing. So at this point, it should still work, right? No? Okay, so the copy does change it, right? If we remove copy, does it work? Okay. So now we do get it. But why does the copy... Why does the copy result in that kind of behavior? Do we overwrite some important thing, perhaps? The IP. It should be a flat structure, right? IP. Oh, yeah, maybe it's this enum thing again. They must be saved some weird way inside of the memory. Is that it? So let's not copy the enum. We are copying to, let's see, the address of IP +1. Or how big is an enum? I don't know that either. But we do have the total size. Let's assume 1 byte. So this is a destination and the source is whatever pp is pointing to, and we want to copy size -1 bytes. Okay, what happens when we run this? Well, it doesn't break this time. So if we go to this, A1 and A2 is equal to 0. Can we perhaps print our arguments and stuff? So what do we have? VM, and we have the instruction. So we have I dot O. Let's just do regular numbers now. And we have I dot args 0. And we have I dot args 1. So I dot O, we have I dot args 0. We have I dot arg 1. Okay, this will give us a little bit more information. So, okay, so the second argument is empty all the time, and it looks kind of okay when we're on the second time. The 1 is okay, and then we have 2, and in this case, okay, we don't have any argument, right? Let's see, we have opcode 1 and this weird arguments. We have opcode 2, and then we have a 2 in the argument. And then we have opcode 3 with a 0. Very weird results. Very weird results indeed. but we should only do this copy step if size is more than 1. Let's do this, and let's also at the same time make a little space here. So easier can see the different times it's called. Okay, so we have a 1 and we have a 2 as the argument. The 2 is there every time. So why is it a 2 there? Where does the 2 come from? Okay, it probably comes from. It must come from the second opcode. So we are off by 1. IP plus 1. Okay, let's just do IP then. But we did that before, didn't we? This feels intuitively wrong. But what are we copying from? PP. Maybe we should keep this. We're copying from PP. But we should take it one step earlier. But then we might run into trouble the first time. Well, let's try it at least. So we have a 1 and a 2, 1 and a 2, 1 and a 2. Am I displaying this bad? IO, IA1, so IA0, IA1, we send the whole instruction. IP, the size is more than 1. And we copy to that structure, position number 2. Are we increasing this incorrectly? So first time size 0, second time size should be 3. So IP is 3 bigger, PP 3 bigger. And how many bytes are we copying? 3 minus 1, we're copying 2 bytes. interesting stuff. I don't see the logic in this too. Where does it come from? IA0. So what if we just were to do IA0 is equal to p plus 1. That's the first 16-bit number. IA1 should be equal to p plus 3 in this case. But we don't have an argument for that, but that doesn't matter. And this should only be done. Let's see. Wait a second. I'm copying this down here. And then I'm executing the instruction in next iteration. Right. Why down here? Because I need the size. So I should put this the last position. And let's remove this for now. Let's see. We need the size for this one as well. So let's put it there. I'm not really sure what I'm doing anymore. Let's see what we I is undeclared. So okay, what's its name then? Should be IP and IP. What's that called? It's PP. Sometimes you get into this kind of zone where you just fail at everything, even though you know this stuff. It's still this weird 2 everywhere. Doesn't seem to make a difference whatever I put inside of my code. It's always this 2. What if we just don't care about this weird structure at all? Let's remove all that stuff. and we reference this instead. And here we will just give pp. This would probably be the same end result anyway, but let's just do something different, right? So instead of an instruction, we will simply have a program P. Let's remove this thing, and instead of IO, we will just do P, and in case 1, we will set A1 to be equal to P plus 1. And same here, we'll set A2 to be equal to P plus 3. Remove. And let's update our signature. And this will be a program star. Okay. So now we're doing the same thing but in a different kind of way. Are we still connected, by the way? Yes, we are. What's this now? 36. Yeah, we can switch for IO. We need to switch for the P. Same here. Instead of IO, we will have P. And what happens now? Same thing. Okay guys, now I know what's wrong. And as I expected, it was a very stupid error that I have troubleshooted for a long time now. If we go to the error function, where I will print the value of the AX register in the VM, this happens after I already have deleted the VM. Pretty lame, huh? So if I take this code and I put it down here instead, and well, and just save. So if run make clean, jump down a little bit, clear screen, run make, and this time, boom. No? 0. Okay, so we're one step closer, I think. So now we get a 0, and we want a 5, right? So if VM, free VM, and this happens before, and we go into the register, looks right. How does this look? I think we are pretty close now. A1 is p plus 1, A1, A2. Let's see when we run the this, what's the argument inside of the A1 parameter? Okay, it doesn't run the move. Why not? Let's see. Execute instruction. Okay. No, that's okay. This is not though. We need to do the actual call as well. And we send the VM. We send the let's see, the opcode pointing to by P. We send arg1 and possibly arg2. I think we got them all. So VM opcode args, VM opcode args. Okay. Now I believe it will work. Yes, now it finally works. So what we did was we ran our program, which will move a 5 into the AX register. It will do a no op, which doesn't do anything, and then it will halt the system. And then we get this. So our virtual machine works. The only thing we need to do is add more functionality to it, and basically add more instructions. For example, I want to get the stack up and running so we can save data onto the memory. And also I would like to add so we can move things not only from static numbers, but from other registers and from the memory as well. But this is all for today. If you like this episode and wish to be notified when I release a new one, please like and subscribe. And also you can enable your notifications by clicking the bell inside of YouTube, so you get an email or similar whenever I release an episode, which is usually during the night every 4th day, Central European summertime. All right, exciting project. It will be interesting to keep following along here. Thanks for watching, and thanks for today.